Okay, welcome all to another class, another session. I think we're wrapping up week number 5 of this semester of the Introduction to Machine Learning course. And we finished last week linear regression. We started with curve fitting, and then we went on to linear regression with basis functions. There were a few more miscellaneous topics in linear regression you'll see on my public site. I decided not to cover them and decided to move on to linear models for classification. Basically, we wrapped up chapter 3, but I did not cover Bayesian linear regression. It's an approach that is interesting, but is not very widely used. We can always cover the Bayesian methods a bit later if we have some time left over. So for now, I decided to move on to linear models for classification. Anyhow, the project that you are doing for project number 1 is a linear model for classification that will allow me to go over the topic a bit with you. And there's quite a few methods for linear models for classification. So we'll cover some of that today, and we also have all of next week to cover linear models for classification. And I understand the project number 1 is due the Monday afterwards. So you have another 10 days or so for handing in project number 1. And you have a session, a breakout session today relating to linear models for classification, I understand from Mihir. Okay, so that's what we have coming up. So let's see, before I put up my slides for linear models for classification, let's see what I can say about the topic. We will talk about several linear models for classification. We'll talk about simple things called discriminant functions, which are not at all probabilistic, which are simply based on figuring out how to separate some kind of a feature space separated by planes, and then we are okay. I see some questions coming in. I thought the project 1 was due October 7th. That continues to be October 7th, right, Meher? Yeah.
Yes, Professor.
Yeah. Okay. That's the same. All right. October 7th is next Wednesday. Is that right? Oh yeah, it is. Okay. All right. So Meher, that's true, isn't it? It'll be next Wednesday then. Today is September 30th already. Yeah.
Yes, Professor.
Hmm?
Yes, Professor.
Yeah. Okay. Okay. All right. I misspoke when I said it's a week and a half. It's actually 1 week from today. Okay. You're right. We are right. Nicholas and Yongwei and Anthony, that the project due is the 7th, right? I'm lagging really hard. All right. Okay. It's not been changed. All right. We're keeping it like that. And I'll have Mihir and Sogata, during your breakout session, you can discuss it a bit more about the due date and that kind of thing. So we'll handle it at the end of today's class. So that discussion on the due date and so on. Okay, so it's they're the ones to look over your project reports and so on. So they will handle what is appropriate. They know the deadlines for this project and the next project and so on. So they can use their discretion about the matter. Okay, so coming back to the lecture proper. So we're going to do linear models for classification. All right, so we're going to do some methods that separate the feature space called discriminant functions. And within discriminant functions, there are several approaches. Some based on sum of squared errors, how best to draw the planes that separate the data points in a two-class case, for instance. And then we also look at a method called perceptrons, which is a famous method, which is the precursor for neural networks. And after that, we look at probabilistic models. And also non-probabilistic models, so on, non-parametric methods, and so on. So there are quite a few methods here, simple to more complex. And logistic regression is also, it's a probabilistic method. So we won't begin with logistic regression and keep that as a continuing topic. All right. So let's go look at the topic of an overview. Okay, so linear models for classification. I'm going to put it on full screen mode. Okay, good. We have linear models for classification overview, right? This is the first set of slides on this topic. So the topics in linear models for classification are the overview. We are beginning with the overview. And then we go into discriminant functions. And after that, probabilistic generative models. Then we have probabilistic discriminative models. So that's a good discussion to have in the early part of the course. Some are generative methods, some are discriminative methods. There is another minor topic called Laplace approximation, which is not terribly central. So what are the topics in the overview? So we begin by, again, contrasting regression with classification, and we are beginning with classification. And we'll talk about linear classification models, what they are, and then converting probabilistic regression output to classification output. So one can use a regression method and convert it into a classifier. And three classes of classification models. Again, those three are discriminant functions and probabilistic generative and probabilistic discriminative. All right, so this is a simple slide that contrasts regression and classification. Supposing we had a data set, on the left side, it shows the age and income and the loan amount. I guess by a bank, the bank is giving people a loan. And this is something, you have a data set you want to learn from. A person with an age of 21, income of 20,000 was not given a loan, but someone was 37 and had an income of 55,000 was given 150,000 loan. So on, and somebody who was 47 and with a high amount, 84,000, was not given the loan. The income was high, it was not given a loan. That's strange. Maybe because of age, and so on. So we have a data set like that. So the regression problem, the output is a number, and we got to say, well, here's a new case. Given the age and given the income, what should be the loan amount? It's a very too simplistic a problem, but anyway, it's a regression problem. On the right-hand side, we have a classification problem where we have age, income, again, the same first two columns, and the loan status is approved or rejected. We have a classification, which is a binary classification. Was the loan approved or the loan rejected? And the output is a class label, and we can think of it as a classification problem. Right? So it's a very simplistic example of regression and classification. So again, this slide continues with regression versus classification. In regression, we assign input vector X to one or more continuous target variables, right? T, so target variables T. And the target variable, if it's continuous, then it would be a regression. And if it is a class or a label, it would be classification. So a linear regression has simple analytical computational properties. In classification, we assign input vector X to one of K discrete classes, Ck, K equal to 1 through K, capital K. And common classification scenarios, classes are considered disjoint. Each input is assigned to only one class. It's possible to think of scenarios where an input can belong to more than one category. Supposing we are doing some kind of text classification, and in comes an input document. And we are trying to say, what kind of a document is this? Is this a sports document, or is this a medicine document, or is it politics and what have you? And So one could say, well, this document is about both sports and medicine. So it's both classes. So we begin by talking about classes are considering disjoint. That is, there's no overlap here. And each input is assigned to only one class. Input space is thereby divided into decision regions. So we're saying the space of X, which is a multidimensional space we have, is somehow partitioned by some boundaries, and saying if it falls in this area, it is this class. If it falls in another area, it's that class, and so on. So in classification, we divide the decision space implicitly or explicitly. So that's what's shown here. Boundaries are called decision boundaries or decision surfaces. If you use something called a decision tree, where we divide the space by one variable at a time. So we say, well, if it's above this value, it is this class. If it is below this value, it's that class, based on just one variable. Let's say the x-axis divides the space like that. And similarly, and then we proceed further, saying once we divide it into two parts, and what if we use one more feature to divide it into two more parts, and so on. And that ends up dividing the space into subparts and so on. And that comes up with some decision boundaries that's more or less like this, where you have some feature divides the space into two parts, and then this left part is again divided into these two parts, and the right part is divided. I suppose I don't know why this is not shown complete, but maybe we divide this one into this and this, and this one again by a partition here, and perhaps some more boundaries over here, and so on. So I guess this one is showing that if it is lies between this axis, maybe we use the y-axis again or something like that, which is keeping it disjoint. So a decision tree, this is what it does. Basically, you're using values to divide up the space and again using them. Whereas some other methods don't work with discrete divisions like this, but like a support vector machine, it's a method which divides up the space like that. And it is based on a Gaussian kernel here. It is a linear method, but the X that you're dealing with is not just the original X. That's the input. We are dealing with some phi of X, some feature of X. And that phi of X, the classifier is going to be linear in that phi of X, but it is a nonlinear function. It's a Gaussian kernel, like basis functions. And when you map it back to the original space, it's dividing the space with continuous boundaries, saying, this is the same problem that we have here, red and blue. And it is more nicely dividing the space into that region is red and this region is blue. It's still a linear classifier. And this one, decision tree, is getting you roughly the same thing. But this seems to be a nicer solution than decision tree. A neural network does a similar thing. We're using lots of parameters, weights, and so on. It is also dividing the space, and we are getting a boundary, somewhat like SVM, where it has been shown that deep neural networks perform better than support vector machines. Support vector machines are considered among the best in their class in terms of how well they partition the boundary. And a neural network, particularly if it's a neural network with multiple layers, deep network they're called, they perform even better than support vector machines on complicated problems. And we say that they have high capacity, that they can separate all kinds of boundaries. There is another method called random forest, which is somewhat like a decision tree, which involves not just one tree, but multiple trees. Maybe that's the explanation to get these more complex boundaries, and it is also allowing you to have some fine variations in this tree structure by using a series of trees called a random forest. And so there are all these interesting methods, all easily available to you online, saying, which one would you like to solve your classification problem? And our task in this Introduction to Machine Learning course is to get some understanding of how these methods work and what are they based on. So obviously there is some basic linear algebra involved in all of this. This is one of my favorite classification data sets. It is called the IRIS data set, right? It's a famous data set that I believe an Englishman, Anderson's IRIS data set, it's called. Anderson went to Canada in the summertime, and in the 1920s or something like that. He went to Canada, and to the northern part of Canada, Nova Scotia or someplace like that. And he was a naturalist, and he went outside and he started observing these flowers, which are really beautiful flowers called irises. And in the Buffalo area, they also grow very nicely. And they only bloom kind of late summertime. And this is the iris flower, a large flower. And he was observing, he was keeping a notebook as to how many types of irises are there here in the wild in Nova Scotia. And he said, okay, there are 3 types of irises. One is called Iris setosa, the one is called Iris versicolor, the other one is called Iris virginica. And he said, oh, okay, there are 3 types of flowers. Okay, and he started taking these flowers and he started measuring some features from them. So these are complicated structures here. There is something called a sepal and a petal. One of them is the petal of the flower, and the other one is sepal. I don't know which one is which. Maybe this part is the petal, and this part is the sepal. And so he measured. He took a ruler, and for each flower, he went about saying, "Oh, the sepal length is 5.1." Yeah, is that centimeters or inches? I don't know. And then sepal width was 3.5. And then, so for each thing, he measured the length of the sepal and the width of the sepal and the width of the petal and the length of the petal. So he had 4 measurements. And he also wrote down what kind of these 3 flowers it was. It was Iris setosa. So, we had here on the left side, they're all Iris setosa, and then we have this is the data for Iris versicolor. They're all Iris versicolor, and then we have here Iris virginica. Those are the 3 tables here, corresponding to the 3 data sets. It's a famous data set, easily available, a small data set. And so a lot of people in the early days of pattern recognition and machine learning played around with this data set, saying, okay, can we write a program that will use this data set and learn from this data set? And so when we get a new flower from somewhere, and let's say we grow one here in Buffalo, and then we say, what kind is it? I would like to know, is it a setosa or a versicolor or a virginica? You would measure the petal length and width and the sepal length and width, and you would run it through this classifier, and it will tell you which of these 3 classes it belongs to. And here is the data that has been plotted. There are, of course, 4 dimensions to this data set, and we are plotting it here on a 2 dimensions here. Those are the base axis. This is a 3-dimensional looking plot on a 2-dimensional plane here on these 2. And there are, of course, 4 dimensions to this data. But let's say in 2 dimensions, what does the data look like? They look like this. I guess, yeah, actually, this is 3 dimensions, right? So this is 1, 2, and 3. Okay, so it's got 3 dimensions here. And we are plotting all this data, the 3 classes. The pluses correspond to the setosa. The greens correspond to the virginica. And the blues correspond to versicolor. And so it looks like this is the result of a decision tree. And the decision tree looks like maybe perhaps this, it went along one particular axis and divided that region into two parts. And each part was again, this part was divided into by a plane along this dimension. And this side of the plane was divided by another one here, and so on. So and so that they could use the decision tree. It says first you divide, is it greater than or less than this value? For instance, it could be greater than 5.1 or greater than 5, less than 5, something like that. And then when you go down the tree, less or greater than a value. So this would be how a decision tree would divide up the space. May not be the best way to divide up the space. Maybe a finer way would draw a smoother surface that is saying, if it is on that side of the surface, it is this class. If it is on this side of the surface, this class, and so on. So those are the things that the more sophisticated methods would do. This would be a decision tree with the linear boundaries, we say. So that was the idea with a simple data set. So linear classification models, decision surfaces are linear functions of the input X, and they are done by defined by d minus 1 dimensional hyperplanes within a d-dimensional input space. And for example, here we have a data set, two-class problem. In this two-class problem, we say that the data is not linearly separable because we cannot draw a plane that separates all of the classes perfectly. So when you draw this dotted line, it kind of tries to do it as good a job as possible, but there is some that is on the wrong side of it, which means you're going to have a non-zero error rate. If you use that and then you try to classify, some of it is going to be misclassified. And then you have here is a non-linearly separable. Here we have three classes actually. And then these happen to be perfectly linearly separable by drawing planes. This is a three-class classifier. And the straight line is a 1D decision boundary in two-dimensional space. And a plane is a 2D surface in 3D space and so on. So when you have multi-dimensions, we call them as lines and straight lines and planes and hyperplanes and so on. Data sets whose classes can be separated exactly by linear decision surfaces are said to be linearly separable. Okay, that's the idea of linear separability. So in regression, target variability is a real number which we wish to predict. In classification, there are various ways of using target values to represent class labels depending on whether model is probabilistic, model is non-probabilistic. So we might end up having a probability associated, saying, the probability of class blue is 0.7 or 0.8, probability of class red is 0.2. So we can have a probabilistic answer in classification rather than a discrete number saying, is it 1 or 2 or is it 0 or 1? We simply have in a two-class problem, we have a probability of 0.9, 0.1. So you can have a probabilistic classification. Logistic regression is one of those which has a probabilistic output. So representing class in probabilistic model, in the two-class case, binary representation is convenient. Discrete t belongs to 0, 1, t equal to 1 represents C1. And t equal to 0 means class 2, and can interpret the value of t as probability that class is C1, probability is taking only extreme values of 0 and 1. So we can have either it's 1 or 0, or we can have any probability associated with each of those classes, as logistic regression does. And for k greater than 2, we can use a 1 of k coding scheme. So this is a very common method that is used where the output for more than two classes, we use a 1 of k coding scheme. That is, the output is not a scalar value, but it's actually a vector t of length k, however many classes you have. So if we have 5-class problem, So an input of class 2, supposing the input belongs to the class number 2, that is, it's one of those types of irises, let's say, and then the output vector is 0, 1, 0, 0, 0, 0 transpose as a column vector. So we say that that input belongs to class 2, class 1, class 2, class 3, class 4, like that. And the value of T sub k, of course, with input data, we can say the probability if it belongs to the class 1, we know that that belongs to that class. But the classifier itself can produce a value such that all these elements here, this vector, add up to 1. Of course, in this case, 0, 1, 0, 0, 0 adds up to 1. But the output could be 0 0.01, 0 0.9, and 0 0.01, and so that they all add up to 1. Somehow it's distributed. So the value of T sub k interpreted as a probability of class Ck. And if Tk assume real values, then we allow different class probabilities. So there's the nice trick. This is called the one of k coding scheme. It belongs to one of the k classes. Although we define it like only one bit can be on for the data, but the output is treated as a probability. Calculate the probability, and you see the power of it. When you have all those classes mixed up and so on, rather than simply saying it belongs to this class, which is a certain probability of it belonging to one class or the other. So representing class non-probabilistic. For non-probabilistic models, example, nearest neighbor, other choices of target variable representation is used. So there are probabilistic and then non-probabilistic. And so there are 3 approaches to classification. We have discriminant function, directly assign x to a specific class using 3 different methods here. Fisher linear discriminant is one, linear discriminant, Fisher linear discriminant, second one, and third one is perceptrons. And this is a famous R.A. Fisher, who was one of the most famous statisticians, who it's named after him. There's a linear discriminant is drawing a linear boundary. But it involves using sum squared errors, minimization, things like that. It also has a closed form solution to be able to draw planes. Fisher linear discriminant is mapping them to a one-dimensional line. All right, so mapping a 2-class problem into a line. But you figure out the best transformation where the data are as separated as possible. So that's a kind of an interesting problem. It's very quickly converts your high dimensional data into one dimension. There's only one value and you're mapping the original value somehow as a projection into the line where they're as separated as possible. Perceptron, of course, is the precursor for the neural network. It is, I like to mention to all my classes that perceptron was invented here in Buffalo. And it was the very first machine learning algorithm that was ever invented was the perceptron, and it was done here in the 1950s. So some of this work goes back to a long time. 50s, what is that? That's about 70 years ago. That's when the first machine learning methods were invented, and perceptron is one of those. And then you have probabilistic models. Probabilistic models are 2 categories again. So you have discriminant functions and then probabilistic models. Among probabilistic models, you have discriminative approach, and then you have generative approach, 2 approaches. In the discriminative approach, we model probability of Ck given x in inference in the learning stage, I should say. So we model, that is given, in inference, okay, this is the result. When you have a input x, you're saying what is the probability it belongs to this class. So that's the probability that is computed in inference. And so it directly computes this value from the data. How do we calculate the probability of a class? And the logistic regression does that. Logistic regression is a discriminative approach, the method you're implementing it. You take an input x, and we need to calculate the probability of the class. So it would involve finding out, for instance, the weights associated with all the features of x. and so that it outputs, and you can apply sigmoid to that, which calculates the probability of the one of two classes from the input W transpose X. And that's giving you a probability of the class. So it's a direct computation of the probability of the class. It's a direct approach. It's called the discriminative approach. And of course, we might be replacing the X with phi of X and so on, but that's a different issue by basis functions and so on. But, we try to figure out what is the best set of weights. It's the optimal set of weights. Logistic regression does the discriminative approach. Another probabilistic approach is, it's a little more involved. It's a generative approach, is to model the class conditional probability density P of X given CK. It says, okay, so you have two classes of data. Of course, in the previous approach also, we can generalize from 2 to 10 classes or 100 classes by using softmax, which generalizes the idea of sigmoid into 10 different classes. Where in the generative approach, if we have 2 classes or 10 classes or 100 classes, it doesn't matter. CK is the classes here. So we model the distribution of X for each class separately. So you say, take your data set for class 1 and figure out what is the probability distribution for X. That is, find out, let's say it's a normal distribution. So there's a certain mean, let's say a variance and so on. We figure it out for each class separately, learn about each class individually, separated out. Then we also use what is the prior probability for each of these classes, CK. So we say, look, are all these classes equally likely? Like the iris setosa and iris versicolor, are they all equally likely? That is, you find equal numbers of these flowers when you went looking for them. It's just how many of each class you had. If they're all equal, you say, well, it's 1/3. Let's see, there was 3 classes there, right? So there was 1/3, 1/3, 1/3. It would be the PCK, prior probabilities. And we would have modeled the distribution of the petal length and petal width and all that for each of the 3 classes. So that would be a learning data set based on what we picked up in Nova Scotia, I suppose. And we would have this is called the conditional probability, class conditionals, conditioned on the class. Then we have prior probability. When you have a conditional probability like this and a prior probability, we can use them together. So apply Bayes' rule, and we can compute this probability that we were looking at earlier on, P of CK given X. So we say C is a class given X. So in the future, when you give me any value of X, I would say I would relate, because I would have known from the learning set this distribution and this distribution, I can put them together and say CK given X is equal to, when applying a Bayes rule, it is X given CK divided by probability of X. So we can apply Bayes rule appropriately, right? It's typically X given CK times probability of CK divided by probability of X. That's what it's going to be by Bayes rule. So you can approach the problem in 2 ways. Is how much weight do I give to each of these features, the sepal length, sepal width, to figure out the probability? That would be the discriminative approach, directly finding that value. The other one is to go about figuring out what are the distributions for each of these classes, and knowing how often you get these, you then implement it, right? So those are 2 different approaches. And if you have lots of data, the 2 approaches will become equivalent. But discriminant approach is a direct approach, and we argue that discriminative approach for small data sets is the better approach, where you're trying to directly solve the problem. And people give the example of different tasks we might be encountered in real life. And for example, you're trying to determine if some language somebody is speaking, what language it is. You just learn what are the sounds of each language, right? So you don't necessarily need to learn the language itself, but you know how it sounds. Maybe it's an Indian language or a Chinese language, or is it English or French? You don't know the language, but you're able to classify directly what it is. Whereas in a generative approach, we say, well, you learn about each of these languages separately and then figure out what probability it is. It seems like a much more complicated approach to solve the same problem, which can be done easier using a discriminative approach. Okay. So separating inference from decision so separating inference from decision is better and minimize risk. That is when you just calculate a probability and associate with it some kind of a loss function. What is the loss associated with making one type of error and the other type of error, and have a reject option. And this would also be able to compensate for unbalanced data. So we could make a decision about the class, not just based on the probability. We could have one more level. Once you get a probability, we could also have a method that says what is the real class based on knowing how sure are you, and using that you make the decision, or you reject it. For example, I'm not going to make a decision because it's so close. It's a reject option. And we can also somehow balance the data, so on. There is all kinds of issues that come up, separating inference from decision. And so anyway, we are not going to talk about that issue about the loss functions and so on here right now on the decision stage. But we'll just look at generative versus discriminative. So model PCK given X in an inference stage and use it to make optimal decisions, and approaches are generative and discriminative. Here again is the equation I was trying to mention to you without writing it down. Here's the equation. P of Ck given X. Bayes rule says P of Ck given X is X given Ck, flipping these two, and then times PCK. This one goes to the separately. So yeah, this numerator comes from the product rule of probability. X given Ck times PCK is nothing but probability of X comma Ck. Joint probability of X and Ck is this numerator. And when you apply the product rule of probability, X comma Ck becomes X given Ck times probability of Ck. Denominator is this X here, is probability of X. And what is this probability of X is nothing but this numerator summed over all possible Ks, right? So you have however many classes, you sum over all of them. And what is the probability of X over all of them? So that's how this denominator is done. You can see that this denominator is a normalization term. So it is used to convert whatever value you get by multiplying these two probabilities. And in order to make that a true probability, you need to normalize it by dividing over P of X, so that when you have overall Ck, the probabilities should sum to 1, right? So it's a normalization term that occurs. And this is the you could actually ignore the denominator completely. When you have multiple classes, if you can calculate the numerator, which you know from the data set, it will give you some value for each class. You can compare the values and say, well, okay, which one has the highest value? You pick that class. That would be ignoring the denominator. But the values themselves, for them to be probabilities, you need to normalize it. Okay, so that's something to keep in mind about generative models. Discriminative models directly model the condition probability Ck given X. So that's the difference between generative models, discriminative models. What used to be the case in machine learning was the important methods were discriminative methods. We say, okay, project number 1 is logistic regression, discriminative model. Could we approach the problem using generative? Yeah, you could. You could do it in this way also, but your performance probably is not going to be as good as your discriminative method, because the data set is not infinite. These probability distributions are not exact. And so you will have a slightly degraded performance. But if you have a lot of samples, sure, generative will be as good as discriminative for the problem. What has happened over the years, let me just mention some of the current work that we do, even for example, in deep learning. is this generative models have become suddenly very popular and famous in machine learning today, particularly variants of it called generative adversarial networks or GANs and so on. They're all generative models. And what those methods, why have they become popular is we have lots of data available in some of these classes. So you're not worried about not having enough data, and the models become sophisticated enough. And sometimes you are only interested in sampling from the distribution. You're not necessarily interested in classification problem. As long as you're able to capture the distribution associated with the data set, you're only interested in picking samples, saying, give me a sample from that distribution. And like, you've looked at all the human faces and just give me a sample face, which would be a face of a person who's non-existent. So people are interested in looking at these kinds of things. Generate for me a new person, or you can say, generate for me some new text. You learn on all of this text. And why don't you go and write an essay on some topic? You can say you can generate the samples from that. So generative models are powerful, like creating new data and so on. That's what they're good for. And discriminative if your problem is simply classification, the discriminatives are the powerful. So there's a role for each of these in machine learning. And in this course, we won't go into the generative models in much depth, other than what is the basic idea of it.
Professor, there's one.
Yeah, go ahead. Yeah, I can't see the chat section. And Mohammed, yeah, tell me what the question is.
So the question is from the previous slide.
Okay, let's just go to the previous slide. Yeah.
So the P of X in the denominator, what exactly is P of X, and shouldn't it be 1?
No, PFX is what is the, so we are trying to calculate when I give you a new X. Here is I've gone to the field and I've measured this flower. I've got 4 values available to me. I have a vector X available, and I'm asking you, what is the probability of each of those, 3 classes, right? That's what we want. And this says in the denominator, you got to put in the probability of X. What's the probability of observing those 4 measurements independent of class? So that is what this quantity is. So what is the probability associated with that set of 4 values? You will have to obtain it from a distribution of all the flowers you have in your data set, irrespective of class. What is the probability? And then we assign a particular probability for that. Oh, okay, that is a high probability flower, or is that a low probability flower? We need to calculate that. So how do you calculate that? It says, well, even if your data is available in 3 bins, pool them together and come up with a probability distribution of that vector, 4-dimensional vector. And when you get a new input coming in, what does your probability distribution say? What is the probability associated? That's what this denominator is. All right. So this is not 1. This is actually the probability of that observation, X. All right. So in the numerator is for each class, what is the probability of that observation? So we are doing the same kind of thing in the numerator, which is for each class, what is the probability of that input you observed? Then we're going to multiply it by what is the probability of that class. There are 3 classes. Are there 1/3, 1/3, 1/3, or is it one is more likely than the other? You take that into account over here. So these are all different things. This is a probability, this is a probability, this is a probability. So we use them all together to calculate this probability. And this formula, where do you get this formula from? It comes from Bayes' rule of when you have 2 variables, X and Y, what is the joint probability? How can you express it in terms of the conditional probability and so on? So it's a Bayes' rule generated formula, okay? So did that answer your question? All right. Okay, shall we move on? Yeah. Okay,
There is
yeah, it's
one
good.
more.
Yeah.
Sorry, Professor. There is one more question by Yusuf. This case for all non-probabilistic models in which must all classes must be disjoint. Can we have joint classes for non-probabilistic models?
Ah, okay, okay. So you are talking about disjoint classes and probabilities for the classes. Yes, we have the samples labeled. So in this case, we are assuming that there is only one label associated with each class. We are saying, we have a grouping here, the iris setosa, and it's only belongs to one class. It is only that kind of flower. Okay, so class is only one of them. But there might be a flower belonging to the other class, the same set of values. That's possible. So you can have, here is another point which got exactly the same four measurements, but it belongs to the other class. It's based on your data set. The data set is saying, I have some of these that belong to this class and the other class, but the label associated with each data is unique. So the data is of that form. So we're assuming that the data is of this form, where there's only one label associated with each data point that we have, and not have multiple. There are ways of dealing with it. Supposing, yeah, as I gave the example of a document being both sports and medicine, in which case that data point X could be either one of those. I guess one way to handle it is put that same data into two in both types of both class conditional probabilities. So that's one way to handle it. I think there are other ways also of doing that, but we are assuming here that there is a unique label associated with every data point. Okay. All right.
That's all the questions.
That's all
Thanks.
the questions. Okay, good. All right. I think it's worthwhile to feel that this Bayes rule is your friend. Okay, this equation is a very useful equation to know, and also it's giving you a sense for you're calculating the probability of a class, and you saw the data, and you're getting a sense why should there be a probability, and this is capturing some uncertainty you have. The data is not exactly falling into separate regions, and there is some mixing going on. So which is why we are calculating probabilities, and what are all the probabilities involved in the problem that is also being told here. So this is all coming into play and all together. Okay, I think this is not a very informative slide. There's a lot in it. In linear regression, we have, oh, okay, maybe it is. Okay, y of x equal to w transpose x plus w naught. That's what linear regression has the form. So take your x and find all the weights and multiply your x by that, and then you add a bias. And then that's going to be your y, where y is a real number, x is a, in Rn, it's in an n-dimensional real space. In classification, we need to predict a class labels or posterior probabilities in the range 0, 1. And you can say the output is of the form y of x is equal to f of w transpose x plus w naught. It's got some similarity to the regression problem. It's a linear regression, we say, because this equation is a linear in x, linear in w. And this one is the same thing, linear in x, linear w. Only thing is, one more thing is added on here, f of that. And so we are saying it's the same thing that goes on in regression, except there is an f associated with it. It's a function. What kind of function is this? And this function could be an activation function, which is like a sigmoid, which is associating this input with a 0 or 1, with a smooth transition between 0 and 1, which gives you a probability between 0 and 1. Logistic regression is replaces f by sigmoid. In logistic regression, which is exactly this function shown over here, is 1 over 1 plus e to the power minus x is this function, which is a sigmoid function. And so f is known as the activation function, and its inverse going back from where you are to the value It's called a link function in statistics. It provides the relationship between a linear predictor and the mean of the distribution function. Anyway, link function is something I have not seen it too often in machine learning, but there is. So anyway, we've already seen what an activation function is. So linear regression and linear classification are similar, except there is one extra step here, which is the sigmoid part of it is going on here. So decision surfaces of linear classifiers. So the decision surface of y of x equal to f of w transpose x plus w naught corresponds to y of x equal to constant or w transpose x plus w naught equal to constant. So there are decision surfaces are going to be obtained, and the surfaces are linear in X, even if F is a non-linear. All right. So we have a linear boundary here, and W transpose X equal to W naught equal to constant is the equation to some straight line like this, and and so surfaces are linear in X. Okay, surfaces are linear in X. The boundaries are linear, even if F is nonlinear, in the sense we have some function defining the value here in the pink region or the green region. And so they are also referred to as generalized linear models. So it's linear in X is the main point. However, no longer linear in parameters of W due to the presence of F. Therefore, more complex models for classification than regression. All right, so this is a slightly more complex model when you're bringing in an F into play. So linear classification algorithms we discuss are applicable even if we transform X using a vector of basis function phi of X. So we could also be using nonlinear functions of X here. And that also brings in a level of nonlinearity on the boundary here. And how do you choose those fees, the biggest issue. And the support vector machines are one method, and other basic methods use like radial basis functions simply use the fees associated with the different data points and so on. Okay, so we're still doing an overview, and so we have overview linear classifier, discriminant functions, two-class, multiclass, least squares, Fisher's linear perceptron. Okay, we already saw what all these things are. I think this is the last slide for this particular section here. Is there are all these. Oh, this just came in here. There are probabilistic models. We are just going to do a non-probabilistic in the beginning. I think the slide is a little bit coming in too early. But anyway, as long as I have it up here, I guess it's supposed to, it's useful because we just talked about generative models and discriminative models. So you see, things above the horizontal line here are generative models. Things below the horizontal line are discriminative models. And you see logistic regression is sitting over here. It is a method where when you have a node that is all filled in, it means you know the value. And in this method, we have to figure out the value of this open node, whose value is between 0 and 1, let's say. In logistic regression, we know all these values. And we are using something called a factor graph here, these squares here, which is somehow a representation of weights that you're going to multiply these with. And you are actually pooling all of this information to calculate P of Y given X. Y is the output, X is the input, and these are some weights you're using it, and logistic regression does this. And we say this is a discriminative classifier, basically, is what you're trying to do. The generative approach to this same problem would have what is slightly different graph. These are all graphs called probabilistic graphical models, PGMs. This is a undirected graphical model, whereas this is a directed graphical model. which involves the same filled in nodes, and we are treating it as a generative problem like we just talked about, which involves calculating the joint probability. And when you have this is called as a Bayesian network, where we say the joint probability of P of y comma x, all of them, is given by probability of x1 given y, probability x2 given y. They're assuming all these variables are independent. That's why it's called the naive Bayes classifier. Naive means you're assuming all the features are independent, right? It's like assuming those flower pet, those values are all independent of each other. One doesn't predict the other one. And so those for all, if you assume all those four are independent, then you can use this kind of a model where you're modeling all these probabilities, and the joint probability of all of these is given by a product of all of them, and from which you can apply, when you know the joint probability, you can always compute from it the conditional probability. What is P of y given x given this quantity? I can first marginalize this and get probability of x, the denominator, and I can calculate y given x, just like we got here. A generative model can also, and this approach is a very popular approach. One of the most famous methods for text classification. When I give you a bunch of words and I ask you, is it sports or is it medicine? Naive Bayes classifiers work very well, where you are modeling for each category. Typically their problems are like this. I need to classify this document. What is the topic about? Then we have a data set. They say here are a bunch of sports documents, here are a bunch of medical documents, here are a bunch of politics documents. And then we calculate the probability for the words given the class. So the features correspond to words. And you would say under each of these class, what is the probability of each word? And we could then, given a new document, and here are some words here, we could say, well, we know the probability for each, under each class, what are the probabilities? We can separately calculate them, and calculate the joint probabilities from which we can calculate sports given these words here, right? So you can use a naive classifier as a simple solution to the problem. And this is the problem of a single decision. So if I give you an input, I'm asking you which class it belongs to. Either you can use a generative solution to it, or you can use a discriminative solution to it. So another kind of problem is not a single decision. You're not making a decision on an input saying, just tell me, is it a cat or a dog, or is it a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9? But I give you a whole sequence now and say, tell me, what does this sequence belong to? This is if I give you a string of characters and I ask you what is the string of characters that it corresponds to. So we might have x1, x2 through xn now correspond to vectors associated with different time steps. Right, here is a word, this is the next word, is the next word, is the next word. And then the goal is to figure out what is the probability associated with each of these words here. Let's say we're doing speech recognition. It's like a different problem than text classification. I've got these sound signals coming in into the microphone. Let's say we are recording it and we want to translate it into printed text. So here is the time sequence, one word sound, and next word is a vector. Let's say every word is captured as a vector, 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 vector. And we don't know, that is the input feature vector. When we don't know what those words are, these have to be inferred. So this is a problem of Y, we use a capital Y. So this is not just a one decision like this case, where we're saying what is the class it belongs to, like what is the class it belongs to here. It is a sequence now, and that is the general version of it from this side is to go to sequence. We get what's called a hidden Markov model. This is what's called as a generative model. This is also a generative model, except we now have a sequence of decisions to be made. And it also takes into account the dependencies. The previous word influences this word. So we're saying there is some connectivity here between what was the previous one. Okay, if we know the previous one, then I have some context in which to make the next decision. So the state, this is what's called as the hidden state. We don't know what the words are. That's what's hidden. We know the sound signals here, but we don't know what the words are. So we need to infer the hidden values here. It is called hidden Markov because there is a dependency between the previous states. So when you have a model which has got these statistical dependencies, it becomes a Markovian model. So that's how in HMM, it's a generalization of this idea. It also is assuming that there is some type of independence going on between the sound itself, but there is a dependency between the hidden states here. So there is some level of probabilistic independence going on, which just like in the naive-Bayes classifier, that the features are independent. This is the feature vectors are independent, but the states are dependent. And another variant of logistic regression to the sequential domain is instead of single decision P of y given x, we are trying to make P of y given x. They're given as uppercase letters saying that y is a whole sequence and x is a whole sequence. And this model does not have these arrows. These two have arrows. Generative models have arrows. They're called Bayesian networks. And these don't have arrows, and they have what are called as factors here. This is called factors here. And they directly compute this probability y given x, just like we said, directly compute, like logistic regression directly computes. This is also saying directly compute this, knowing these dependencies. And this particular model has a name, which is, all right. My real estate of my laptop is small, so sometimes what happens is I got things sitting on each other. Okay, it's called a conditional random field, CRF. This is a very famous model. What was happening in speech recognition and other domains for a long time, before the advent of deep learning. Let's say 15 years ago, what were the things that were used to do speech recognition? And the models they were using first was the hidden Markov model. They said, wow, hidden Markov models are the best. They work very well for speech recognition and any other sequential type of problem. Machine translation is a sequential problem. In some way, it's more general. Like, let's say we are observing something in German over here. This is all German. And what is the English words here? But it is subject to simple limitations. It's only depending on the previous word, so on. So machine translation or transcription from speech sounds to classes and so on. Those would all be, HMMs were the best. And then conditional random fields suddenly became better understood. It's like, oh, this is nothing but generalization or logistic regression, and this works much better than HMM. CRFs work much better than HMMs. And why? Just like logistic regression works better than naive-Bayes classifier, right? When your training data sets are not infinite and so on, right? So in practice, it uses the data better. Same thing, CRFs uses the data better than in HMM. So these became the best models for sequential problems. And moving on, today, what do they use for speech recognition or machine translation? And these all have been replaced by deep learning networks, where you have this becomes a discriminative model will become a convolutional neural network or a CNN. And this one becomes what's called a recurrent neural network or an RNN. And there's a even that is being replaced by today by other models like attention-based models and so on. So this machine learning is a constantly changing, developing field, and we are kind of looking at these simple ideas here just to fix these ideas. Okay. All right. So let's do away with this one here, and okay, we have. Oh, how are we doing on time, Mihir?
Professor, we can start with the breakout sessions now.
Okay, already. All right. We only covered one. I was planning on 1 and 2 today. All right. So we'll continue. No hurry. Hopefully, my general discussion rather than getting into all the math right away is helpful to get you a sense for where we're going, So, all right. And Mihir is going to, and Saugata will help you with the coding issues. And today, I think they plan to cover more on linear methods. Okay. All right, then I'm going to make Mihir the host. All right. Okay, Mihir, you're in charge and have a great time. I understand the breakout sessions are going really well and students are spending a lot of time on it. All right, hope you are able to do that. Okay.
Okay, Professor.
Yeah.
So the class, I have shared the Google Drive link in the chat section, and it's also available